Hi everyone, my name is Qingyuan. Today I'll talk to you about SEISMIC, a self-exciting point process model for predicting tweet popularity. This is joint work with Murat, Hera, Anand, and Jure, and we are all from Stanford University. So first, let me introduce you the main object of this today's talk, information cascade. So you can see on the left side, this is a real cascade. It's basically just a series of waterfalls. So there are 1, 2, 3, 4 stages of this waterfall. And usually you can see the waterfall becomes wider and wider as it coming down. And we can see there's an analogy between this cascade and how information spreads. So here's an example of an information cascade. It's referred to the situation that a large number of people engage in the same action. So usually it starts with just small groups of people, and then these people spread this message in the network, and more people are engaged in the same actions. Twitter, what we study, is actually a very good data set for information cascades. So basically, an information cascade in Twitter consists of one tweet and a sequence of retweets. So it starts by a Twitter user post a 140-character message, which can be seen by his or her followers. Then, if his or her followers decide this is interesting, they can further retweet it and share it with their followers. So here is a pictorial illustration. This is the original tweeter, and he has 5 followers. These 2 followers thought this is interesting and retweets, and there are more retweets coming on. Our goal in this talk is to predict cascades in real time. So more specifically, given the tweet and retweets up to some time t, we want to predict its final popularity. There are few applications. The first is we can use this prediction to rank the content, so the Twitter user can read the information more efficiently. A second application, we can use this prediction to detect viral or breakout tweets just shortly after they're posted. This can be helpful to make trending topics. Third application, we can use our model to understand how humans actually behave in a social network. This can be very valuable for social scientists. So let me give you a more formal definition of our problem. So here are 2 sequences of data that we will be used in SEISMIC. The first sequence is the retweet time relative to the original tweet. So the original tweet is T0, it's always 0 in this notation, and then will be T1 and T2. These sequences give us a stochastic process which counts the number of retweets by time t, and I will use capital RT to denote that. The second sequence is the number of followers of each retweeter. So N0 is the number of followers of the original poster, N1 is the number of followers of the first person who retweeted this, and so on. And this also gives us a stochastic process NT, which is the number of exposed users by time t. Given these 2 sequences, our problem is formally defined as, given these 2 sequences from time 0 to time capital T, can we predict the final popularity denoted by R infinity? There are several existing approaches to cascade predictions. They can be broadly categorized into 2 groups. There's a feature-based method and point process-based methods. The majority is actually the feature-based methods, which requires 2 steps. In the first steps, you do some feature engineering. You extract a large number of features, hundreds of features, from each cascade. They can be temporal features, they can be about network structure, they can be about what this tweet is about, or about the user who is involved in this cascade. After you get all your features, you can use a big supervised learning method to construct a regression model and use that to predict the future. The second group of methods is point process-based method. So this is based on point process. It's basically just a counting process in our problem, which counts the number of events up to some time. There are some existing works that use dynamic Poisson process and reinforced Poisson process, which are just variations of the Poisson processes. What we use is a self-exciting point process, which we believe captured the mechanism of how information spreads over the social network more accurately. So here's an example. So this is a funny tweet that we found in our data set. It's interesting both because it is a joke. So there's very controversial about Justin Bieber on Twitter. Somebody liked him, and there are some people really hate about Justin Bieber. And this tweet went really crazy among the haters. And for this tweet, it's also interesting because if you look at how it spreads over the network, I plotted the retweet count, the histogram over time. You can see in the beginning there's some retweets because the original poster had some followers, but then it was dying down. Then after about 20 minutes, it started to go very crazy. It started to become very viral and last for a very long time. And on the bottom, I show you the prediction by SEISMIC. The red horizontal line is the final number in the end, and the bottom blue dashed curve is the cumulative number, the capital RT. You can see this actually converged to that number at a very far time. And our prediction is actually fairly accurate from 1 hour. So before walking you through the details, let me summarize some highlights of our SEISMIC model. It is short for self-exciting model of information cascades. We use this name because originally the self-exciting point process was used to model earthquakes. So we thought this is a cool name because they also have information cascades. SEISMIC is a generative model about how information cascade forms. It has a very easy interpretable parameter called infectiousness that I will introduce later. It is very fast, it's scalable. The prediction is linear in the number of retweets that you have seen, and it achieves the state-of-the-art performance. First, I'll give you some background about point process to introduce the self-exciting point process. So for all the point process models, the crucial thing to model is the intensity. You can think it as the expected number of retweets in the next unit time. Here are two examples of point process. The first is just a homogeneous Poisson process that your rate lambda t is equal to a fixed number lambda. This is not really good for information cascades because you can see there are a lot of variations over time. There's another example, reinforced Poisson process, which is recently proposed to model information cascades. So there are three components in the reinforced Poisson process. The first is about how viral the tweet is, P. The second component is function over time, and it's actually a probability distribution and usually decays over time. The third component is G of RT. It is used to model the rich get richer phenomenon. So usually as your RT gets larger, this part also gets larger. So the more retweets you have, the more likely you will receive a new retweet. Still, we found this is not particularly targeted at how the information is actually spreading. So they're not really suitable to model viral tweets. So if you want to come up with a successful model of the information cascade, you need to consider the mechanism behind each retweet. We think there are mostly two key steps of retweeting. In the first step, the Twitter user need to track the Twitter and find this tweet on his timeline. In the second step, he went through a mental process and need to decide if he wants to retweet this and share it with his followers. So for the first step, we use a power law distribution to model it. It's also called memory kernel in the literature. In the second step, we introduce this concept of tweet infectiousness. So here is a self-exciting point process to model information cascades. Here there are two components for the rate lambda t. The first component is as a p, it's just the infectiousness, or you can intuitively think it as the probability of retweeting. And the second component, this is the self-exciting part, that all the retweets that happen before time t has some influence. That's why it's called self-exciting. For each of the retweets, the influence is proportional to the number of followers that retweeter has. And it's also proportional to a function that depends on how long has it passed since the retweet is posted and the current time t. And you can think this whole part as the rate of viewing. So this is just the probability of retweeting times the rate of viewing. However, if we just summarize all the tweets, or just we summarize an individual tweet by just a single number p, that's not very enough for viral tweets. So here is the example I showed you before. This is a histogram that you have seen, and this is the infectiousness p estimated by our model over time. You can see as this tweet becomes viral, the infectiousness actually increases quite a lot, and it stayed at a very high level for quite a while. So it's not enough to just use a fixed number p to model a process. What we do is SEISMIC replaces p by a smooth process p of t. And this is a result of the estimated p of t for this tweet. So how do we estimate this parameter p of t? We use a local smooth version of the maximum likelihood to estimate this parameter. So intuitively, you can think this estimator is a ratio of the number of retweets divided by the number of views. And this number of retweets and number of views are weighted by this kernel k. Basically, you give more weights for the retweets that are closer to time t. After you obtain an estimate of the infectiousness, you can use it to predict the final popularity. That's our eventual goal. So this slide, this is the prediction formula that SEISMIC used to predict the final popularity. We assume we know the mean network degree n star, and we assume the infectiousness is already become very stable and will remain. It will remain a constant from time onwards. So here we give the expected number of the final size given all we have seen up to time t. So there's an interesting phase transition phenomenon. So there's the threshold 1 over n star. If your parameter p is greater than that threshold, then theoretically that information cascade will blow up to infinity. Of course, that doesn't happen in reality. In reality, if your p is greater than that threshold, it will eventually comes down and stabilize at some value less than the threshold. So we will wait till it stabilizes and use this formula to predict. You can see our paper for the derivation of this, which uses branching process theory. So here is the example that I showed you before. Notice that in the first 1 hour, we are not able to make a prediction because remember we have this infinite number if the infectiousness is greater than that threshold. However, even if we can't make a prediction, we still know at that time this tweet is very viral and we can keep a close eye on it. Okay, here is the experiments that we run for SEISMIC. We obtained 1 month of Twitter data set in 2011. There are really a lot of tweets in 1 month, and we filter them by these criterions. First, we only consider the tweets that are posted in the first 15 days. So we have at least 15 more days of observing retweets. Second, we only consider English tweets because there are some inhomogeneity across different languages. And we only have, in our model, we sort of assume everybody is homogeneous. So we only consider English tweets in experiments. Third, we consider tweets that doesn't have hashtag. So they're spread purely through the follower network. And finally, we consider only the popular tweets, which are the more difficult tweets to predict. We ended up with about 166,000 cascades, and they're in total over 34 million retweets. In this data set, we compare SEISMIC to 4 other baselines. The first 2 baselines are based on regression. The third and the fourth are based on self-exciting, not self-exciting, but the ordinary variation of the Poisson process. Here's the first metric that we consider, the absolute percentage error. It's just the absolute difference of the predicted value and the true value divided by the true value. So we plot the median of the absolute percentage error of all the cascades over time. You can see our SEISMIC model give you much more accurate prediction than all the other baselines, especially in the beginning where everything is actually the most interesting and the most difficult. For example, at 1 hour, SEISMIC has about 15% median error, and all the other methods have about 25%. In the second metric, we see how SEISMIC cover the top tweets. So we create a list of true top 500 tweets that has the most number of retweets in that month. And for each of the prediction method and each time, we can predict the retweets and get a top 500 tweets that has the most predicted value. And we see how that two lists overlap. So here is the coverage plotted against the fraction of observed tweets. And you can see when you see about 25% of the retweets, we have about 70% coverage, and all the other methods have less than 55% coverage. So to wrap up, our SEISMIC model is a very effective model of information cascades by using the self-exciting point process. We have efficient algorithms to update the parameters and make predictions. SEISMIC also outperforms several other baselines and state-of-the-art. You can find the code and data. You can find data and code available at our website. Thank you.
Questions?
Have you thought at all about how to extend to the case where you have hashtags?
So I think that requires a model of hashtag as well. So basically, you can add an additive term to the part that we have, and that's the contribution of the hashtag. But really, you need to join a lot of the tweets that have the same hashtag, and basically predict or model the infectiousness of that hashtag, and then add that to each individual tweet. And I think Twitter also has some algorithm to rank those tweets inside a hashtag. So you need to also consider that, because if you are on the top of that hashtag, then there are more traffic. If you have the hashtag but you are in the bottom, then there won't be many people seeing it. So yeah, it can be extended, but it requires a more sophisticated model.
Great. Any other questions? Yes.
So did you compare your approach with a model which is trained by boosted trees with a large number of features?
So ideally, our model, you can use it as one feature in the feature-based method. So I haven't compared it with the feature-based method because you can see we only use 2 sequences. So I think it's not very fair to directly compare them. I think a more fair way is to add our prediction as a feature in those supervised learning methods and see how much does our feature contribute.
So do you believe that your model will be a good feature in different models trained?
Yes, I believe it.
Thank you, I see.
Great. Any other questions? Oh, one more.
Yeah. So have you thought of varying R infinite? So I assume that you are taking the next 15 days and then trying to predict the popularity at the end of the month, right?
Yes.
So if you make it like 45 days, 2 months, so how does the accuracy change? Are there any effects?
So right now we can use like a sort of a supervised way to learn some constants to discount for the time that we want to predict. So if you just use the theory directly, there will be a very hard integral for you to compute if you want to predict for the next 1 hour or 1 day or a week. So we only did it for infinity, and we used 14 days as approximation for that because it gives us easier formula. And it should be suffice to all the practical usage, I think. Yeah, hope that answered your question.
Thank you. I know there was another question, but we have to move on, so we'll take that offline. Thank you very much again.